All right, it is recording. We'll return in just a moment and ask you if there are any questions. And as promised, are there any questions? Okay, let's do it. Return those. We last left off with, we had done magnetic field inside a solenoid. What was the very last thing we did? Or what's the last thing in your notes? Or did you take notes?
Just then when we were talking about, figuring out direction and everything, it was still more right-hand rule stuff. I have something about lens written in here.
Something about winds?
Lens?
Lens.
L-E-N-Z, something like that.
Oh, Lens. Lenz's law. Faraday Lenz's law. Okay. So we have an EMF that is produced, in essence, a voltage that's produced by having a change in the magnetic flux. So this phi sub B is the magnetic flux. And that's just the sum of all the B dot A's. So if I have an open surface and a magnetic field going through it, in the simplest case, the magnetic field goes through the entire area, and it's just the magnetic field times the area if the magnetic field's parallel to the area vector or perpendicular to the surface. And then, I guess we went into the explanation of what the minus sign means and the fact that the induced EMF produces a current, which I'll sometimes refer to as the induced current or the secondary current, which properly grammatically that opposes the change in the magnetic flux.
Hello.
Welcome.
Thank you. My shirt's fun enough.
Oh God, Friday.
I know.
Forgot.
Hey, you weren't
Man.
glad. That's better than that.
No, yeah, this is my work. Yeah, so I was supposed to bring in a different shirt anyway. You and I just have to work.
I
Forgot.
appreciate it. I apologize.
I made an effort.
Yep.
Hey, the shirt is
Noted.
cooler than it lets on. Can I share the brief story?
Yes.
I befriended the breakdance crew in Cozumel once, and they gave me a t-shirt.
Oh,
Highly
wow.
recommend if you're ever there. They're super cool people.
And where
Helps
was
to
this?
know some Spanish, but
What group was this?
the professional breakdance crew on Cozumel, Mexico, Cozumel Island.
Okay,
They're very fun.
all right.
Yes.
And a tip for our international audience there, for anyone who happens to be down in, I guess, Cozumel Mexico. All right, let's do an awkward transition back to physics.
Not bad.
All right, so the induced EMF, and so we spent some time with the right-hand rule trying to just sort of examine which direction the current would flow, using, of course, a right-hand rule. So let's take a look at another situation known as the motional EMF. And so you'll see if you look at, I guess Masterson's gonna have one, there's gonna be a number of problems where I've got a bent wire and then another wire on top of it. So this wire, and let's, as you know, stunning, absolutely stunning visual effects. The red wire can move freely on the other wire. The purple wire is one wire that just has two right angles in it. And of course, we gotta throw a magnetic field in, because otherwise, why would it be in this chapter? And as usual, the magnetic field coming out of the board. So I'll just put a bunch of dots here. And we are approaching our Princess Bride reference. So L and W are dimensions here, so I guess the part that's parallel to the red wire is length L, and the part that's perpendicular to the red wire to the part parallel to the red wire is length W. And I'm willing to bet that the visual image there really beats out my words. So, what is the magnetic flux going through the closed loop? Assume that there is contact here between red wire and purple wire, that they are in touch with each other. They're not insulated wires where I just have one thing sitting on top of another. There's actually a full loop. There's nothing running through the current, nothing running through the loop right now. There's no current involved. But right now I just got two sets of wires touching each other. So what is the magnetic flux through the area? Do you need numbers or?
It's still B times A.
And what is A?
Is
L
it,
times W?
Yeah. So our magnetic flux, B dot A, which is just the magnitude of B times LW.
so even though that's an open shape, it's still going with the standard area? Like rather than like,
Right, it's the area can change by just easily by moving this wire here, but this is still a closed loop here.
Okay.
Now, I want to induce a current. I know that I can induce a current by changing my magnetic flux. And since magnetic flux is based upon the magnetic field and the area, I can change one or the other, or both. In theory, I could also change them both in such a way so that they cancel each other, so that the total, or the magnetic flux, stays the same. But let's not worry about that right now. So because my magnetic field is coming from some external source, let's assume I don't necessarily have easy access to it, but I can move this wire quite nicely. So what I'm gonna do is I'm gonna move this wire outwards at some speed V. Or since there's a direction there, at a velocity V, with the vector symbol. But the important thing is that I'm moving the wire and I'm expanding my area. So therefore the what's happening to the magnetic flux?
Should be increasing.
And therefore, the current is gonna try to do what? The induced current.
Do the opposite.
Okay. That works. So my speed here, let's assume it's constant. My speed is just the change in distance over change in time. So V is equal to dW dt. Oh, sorry, wrong group. Delta W over delta T. With W just being the distance from the left end to where the red wire is. So let's go through step by step. I'm gonna figure out the voltage here. I'm not gonna worry about the negative sign because we've already figured out the direction. Actually, let's go ahead and do that. If the magnetic flux is increasing, because I'm increasing the area, and the nature doesn't like that, which way will the current flow? So clockwise.
Because it's coming out of the board and we want it to oppose it by going into the board. And if you point your thumb into the board, your fingers curl clockwise. Is that right?
Yep. So current's gonna flow like that. So in this wire here, it's gonna flow down. Let's look at it from a slightly different point of view, because if you forget that right hand rule, don't forget, we have plenty of others. If I have a wire going through a magnetic field to the right, so try that wording again. I have a wire moving to the right through a magnetic field. In nature, heats change. I'll sort of do it through the back door here. If I have a current flowing down through this, and the magnetic field's coming out, which way will the force on this wire be?
Can you say that one more time?
We've talked in the past about if I have a wire with a current running through it, and I got a magnetic field, and this wire is bathed in a magnetic field, that there will be a force on that wire. The question I'm asking is, if I have a current flowing down through a magnetic field that's coming out of the board, which way will the force on the wire be? You could also think about it as positive charges moving in the direction of the current. So if I have a positive charge going that way and the magnetic field coming out, which way will the force on the charge be? And this is when Harrison would pull out his stem gun. All right, when you're doing the stem gun, which way does the finger point?
Down.
All right, so down, direction of the positive charge or the current. Which way do these three fingers point?
The direction of the magnetic field.
What does the thumb tell you? More specifically, what's going left?
Force? The force?
Yeah, the force. So this wire is going to be forced that way. So as I pull this wire out, the current is also being induced, not only to reduce the magnetic flux, but the current is also causing a force back that way. And again, good thing, if the force were in the direction of movement, all I'd have to do is take this magnetic field, let's say the Earth's magnetic field, I'd set up a little wire like this, and I just give it a little tap. If the force is in the direction of movement, then that thing can get faster and faster. Just grease that up a little bit. Suddenly, I just need something long enough in order to get a projectile going. And of course, we're back to weapons. So we have a current that will be going down through this wire and around. So I'm not going to worry about the direction. So all what I need to do is look at the change in the magnetic flux, which is V times A, over the change in time. So now I have a change in the product of two things. Now, in this particular case, I know the magnetic field is constant, so it can factor out, but let's think about this a little bit more generally. Anyone in here in Calc 1?
Taking Calc 1.
Staying away from it.
You're staying away?
Staying away from it.
If, I assume you've gotten to what that would be?
Talking about derivatives?
Yeah.
Yeah.
So what would this be? I guess Freddie, you nodded also.
I took it like 2 years ago.
Okay.
I took it like 10 years ago, literally.
Okay, so we got half the class here. Nancy, where are you in
I
math?
took it like 2 years ago too.
Say it again?
I took it about 2 years ago too.
Okay, so Wesley, you're just,
Never took it.
okay, anyone besides Wesley?
Nope.
You're off the hook?
I could have been using calculus most of this time.
Oh, no,
Man.
I could not. Those are repressed
What would this
words.
be?
Just the derivative of BA?
What is that? It's a differential of BA actually, but
Yeah.
if I did it over dt,
Is this
Okay.
where you put like the summation symbol and then there's like little something above it and below it that needs to be listed?
no,
No.
with calculus, you don't need to do that, but,
Oh.
all right. So apparently, Wesley did not lose out on anything.
No, we didn't.
BDA plus ADB.
Oh, okay.
Yeah, probably, I don't know if I've told the story, I was in in an economics class, and there was two of us who had calculus in there, and the professor kept pointing to one of us to say, and what would this be? And I'm going, I don't know what you're looking for here. And then he'd show it, I'm going, oh, of course, why? And then I found out there was a third person in the class who had taken calculus, but he was keeping his mouth shut and just
Why?
didn't want the professor to know. Anyway, when you're given a change in two things which potentially could change, it's one of them times the change in the other plus the other times the change in the first thing.
I think also known as the product rule, I'm pretty sure.
Yeah, it is the product rule.
Is this something we'll be expected to know, this relationship? Or is this kind of just to explain something else?
It is. Yeah. I don't know. Because there's a problem I've had before where I've had changing magnetic field and changing area. And I can't remember if I did it for 152 or if that was a 252 problem. So anyway, I've got this sum, I have two terms divided by a common denominator, so we can break that up. So B, change in A over change in T, plus A, change in B over change in T. All right, so that's just in general right there. And again, I've ignored the sign because we've already thought through the direction of the current. Therefore, we can actually now simplify it. Which of these two terms is equal to 0?
Well, the magnetic field is constant, so the change in B should be equal to 0.
So we'd have this, our EMF has now been reduced to that. And area, as we established earlier, is just length times width here. And so the induced EMF, the induced voltage, is now equal to whatever the magnetic field is times the change in the area, which is length times width over time. And hey, there we go again, we got another one. Do a quick little practice here. So that's B times, I'll help you out, I'll do the delta T on the bottom.
B times the change in L, wait,
Just looking at this piece right here.
W,
Sorry, W.
then plus delta W.
got it.
Which becomes B times W delta L Let's see if I can actually write that worse. W times delta L over delta T plus L times delta W over delta T. And so we got delta L over delta T, delta W over delta T, which either of those 0?
L's not gonna change.
So we're left with B L delta W over delta T. Now the Princess Bride reference, that's just the speed. So we get BLV, BLEV. It is not true love, it is BLEV. Now, if you have no idea what I'm talking about there, you need to watch the movie again or watch the movie for the first time. Even if I hadn't talked about this, you should still see the film.
Just out of curiosity, is that something that like young people watch these days? Has anyone here seen it?
Seen what?
See what?
Princess Bride?
Oh, I've seen Princess Bride.
Okay, no, have you?
Is that from Princess Bride? Cause I don't remember that.
that.
See, because when I taught middle school, and those kids would be basically college age now. Or is that 10 years, so they would have graduated from college, they would have just graduated, so they'd be in their early 20s. That they were gonna have a movie night, and I said, how about Princess Bride? And the person who was organizing it said, everybody's seen that 1,000 times. And so that's why I'm still figuring that everyone in here has seen it, but apparently
It's changing.
it is changing.
Is that from, I didn't know it was from that movie. I've only seen it one time. Sorry. Only once.
Well, that's better than some other people.
As long as you can get the inconceivable reference, like, you're okay.
It was Andre the Giant's greatest role.
Yeah. Well, and that guy, that Mandy Patinkin guy, he played in Criminal Minds, so I do remember him. He's the guy with the sword, right?
Yeah, well, that describes several of them, yes.
Yes.
Andy Dickens
What was
in
his
there.
name? I can't remember what his name in the movie was.
I don't remember the character's name, I just remember Inigo Montoya.
Yes.
He was
Yes.
my father.
Yes.
And we're back to weapons again. Any questions up to here? We're about to do a plug and chug, but any questions about